Hi class. I promised you in class that I would come back to this discussion of torque on current loops, that we would spend a little time connecting the things that we're learning about, namely the forces acting on individual lines of current, to things that we learned about first semester, namely torque and rotation, because we've been talking about three-dimensional distributions of current, loops of current, and then when you apply forces to loops of current, you can get forces pointing in different directions, and as a consequence give the loop complex behavior that you can make them rotate. Okay, so these things are all connected, but it's worthwhile revisiting things that you learned about first semester and working through how we connect them to things that we're learning about this semester. So I'll remind you that you had originally learned to define torque in the following way. We write it as a vector equation. Torque, which is itself a vector, is equal to this vector r cross this vector f. The vector r is the so-called lever arm. It is a vector that points from the point of rotation to the place where the force causing the rotation actually is applied to the physical object. Okay? The consequence of that force being applied is that the object experiences a torque, which is a applied force that causes a rotation. Okay, and so that torque is a vector. That vector is defined by the right-hand rule. So if the object rotates in a given direction, you use your right hand, you point your fingers in the direction of rotation, and your thumb defines the direction that we call the torque vector. Okay, so you've encountered the right-hand rule before, and you may or may not remember that from first term. So the magnitude of the torque, which is the thing that we numerically compute, the right-hand rule gives you the direction, but the numerical magnitude of the torque is defined to be RF sine of theta, and I usually prefer to group those in the following way. I will often group it as R sine of theta times F, or sometimes I will group it as it was originally written as F sine of theta. And the reason we do that is because what matters in the torque equation is not the pure distance from some point on the object to the place where the force is applied. It's actually the perpendicular distance from the place where the force is applied to the axis of rotation. And depending on the geometry of the system, there will be an angle that relates that all together. And so this r sine of theta, for instance, is the projection that gives you the perpendicular piece of the lever arm, not the pure lever arm that goes from the point of rotation to where the force is applied. Okay, so you learned a lot about that first term, and if that seems unfamiliar to you, you should go back and review it. So for the moment, let's just bear that in mind, and let's go and let's apply that to the current loop case. Okay, so with a current loop, we want to define a loop and a magnetic field that we're going to be talking about. So you can do this with any shaped loop, but I think the physics of working it out is a little bit easier if you work with a square loop. So let me define a square loop like this. Okay, so it will have sides of length, let's see here, let's call the vertical side length A, and let's call the long side this way length B, and then we want to immerse it in a magnetic field. So I'm going to have a magnetic field that points from the left to the right. Okay, and so this is the magnetic field with magnitude B. Okay, now this is just a wire loop. The way I've drawn this, there's not going to be any forces that this loop feels. But if there's a current flowing around this loop, let's say we have that current flowing clockwise around the loop, then we can ask the question, what does the force that any given side of the loop experience as a consequence of being immersed in this magnetic field? Okay, and we know how to compute that. We've learned that. We've learned that the force, the magnetic force that a current loop feels, is given by I, the value of the current, times the length of the wire that's immersed in the magnetic field, times the magnitude of the magnetic field times the sine of theta, where theta is the angle between the direction the current flows and the direction that the magnetic field points. Okay? So let me label the sides of the loop here to make our lives easy. 1, 2, 3, 4. Okay? And sides 1 and 2 are not too bad. Okay? Sides 1 and 2, in this case, the magnetic field is parallel to the current. And down here for side 3, the current is anti-parallel, but still parallel to the direction of the magnetic field. So up here, theta, which is the angle between the current and the B field, is 0. And down here, theta is 180 degrees. And so for both 1 and 3, the sine of theta is 0. Sine of 0 is 0. Sine of 180 is 0. So in both these cases, the force is equal to 0. There is no magnetic force on the current when it's on those two sides of the loop. Now, it's considerably different when I look at the two vertical sides. So on this side, the current's flowing this way, and on this side, the current's flowing this way. So if I begin with just the right-hand rule, let me look at that first. So here, I take and I put my fingers in the direction of the current, so pointing towards the bottom of the page. I turn my palm so that it's facing the direction of the magnetic field coming out of my palm, and so when I curl my fingers, then my thumb is pointing up out of the page on this side. So that's the direction of the force on this wire. And if I do the same thing over here, my fingers go in the direction of the current, my palm has the magnetic field coming out of it, and when I close my fist, my thumb is pointing down into the page. So here, on this side of the loop, the force is pointing down. In this case, the angle between the current and the magnetic field on this side, okay, so the current's flowing this way, and I go 270 degrees to get to the current, and on this side, I go from the current to the magnetic field, I get theta is 90 degrees. And in these two cases, the sine of 90 degrees is plus 1, the sine of 270 degrees is minus 1, okay? So that gives you, the minus sign difference gives you the fact that the force is pointing up or the force is pointing down. That is, they're pointing in opposite directions, which we knew because we'd worked that out from the right-hand rule. So for current 2 and for current 4, the force here is I times the length of that side times the magnetic field times plus or minus 1. Okay, and so the length of these sides is the length A. Okay? Okay, so those are the forces involved, and forces are just part of what we need to calculate torque. What's the other piece of what we need to know? Well, we need to know where the loop is going to rotate. Now, one of the things you probably remember from first semester is that when you have a symmetric object and you apply equal but opposite forces on the opposite sides of the object, then the object rotates around its center line. So this loop will rotate about a center line like this. And so if I take that center line, the lever arm, that is the distance from the axis of the rotation to the place where the force is applied, in this case, the force is applied on the current over here on the edge of the loop, or the force is applied on the current on this edge of the loop. That lever arm, in this case, for both forces, the force on this side or on this side, is half the length of the loop. So, if I take that lever arm, the torque on side 2 is equal to RF times the sine of the angle between the lever arm and the force. Well, the force is pointing straight up and the lever arm is pointing straight out, so the sine of that angle is 90 degrees, so I'm not going to list it. So this is just B over 2, the length of my lever arm, times my force, which is IAB. Similarly, the torque on side 4 is RF, which is again B over 2 times IAB. So the total torque is the sum of those two. So it's IAB times B over 2 plus IAB times B over 2, or it's IAB times B. And if I regroup that, I get IB times AB, but AB is just the area of that loop. So this is I, the current flowing around the loop, B, the magnitude of the magnetic field that it's immersed in, times the area of the loop. That is the maximum torque that this loop will experience. If you imagine taking the loop in any other rotation around that axis there, then you will find that the lever arm decreases. And it's only maximum when the loop is parallel to the magnetic field like this. So we will use this formula when we need to calculate torques as the maximum torque that a loop can experience when it's immersed in the magnetic field. Okay, so we'll come back to this. You'll do a little bit of this on homework, and I'll do an example on video, and we can talk about this if you have some more questions. Okay, good luck everyone. We'll talk to you soon.